Good evening, everyone, and welcome to the latest of the Wednesday evening technical talks by members of the UK Microwave Group. And this evening, I'd like to welcome Brian G4NNS, who will be talking about backyard hydrogen line astronomy. Just a little bit of background about Brian before we begin. He was first licensed in 1967 as G8AZU, Alpha Zulu Uniform. He soon became interested in microwave operation with gun diodes for transmitting from hilltop and mountaintop locations. And he held the UK record between Snowdon in GW to Cairnsmore of Fleet in GM in 1973, and I take it that was on the 3 centimeter band. Now Brian is mainly active on microwaves, including EME on 3.4 to 24 gigahertz. Brian has held the post of chairman of the UK Microwave Group, and he is one of the main organisers of the 2012 EME conference held at Cambridge in the UK. He's also helped to build a number of microwave beacons, and he does have 5 minutes of fame with Michael Portillo whilst he was at Goonhilly, and he's still awaiting payment for his appearance fee from the BBC. Another interest of Brian's is astronomy. So combining his interest in radio and astronomy has led him to using his EME setup for radio astronomy. I'd like to hand over to Brian now, who will give his presentation. Over to you, Brian. And you, yeah.
Right. Well, good day, everyone. Let's see if we can get this presentation going. And the first thing we need to do, I guess, is to share the screen. And mysteriously, I am not seeing anywhere on my screen at the moment to cause it to share. I don't know whether you can indicate to me, Neil, whether in fact we are successfully sharing, but I am not seeing the usual green tag. Let me just come out of this momentarily.
No, we're not seeing it at the moment, Brian.
Okay, right. Okay, let's start again. Hopefully you're seeing something now. There we go. Okay.
Yes, that's okay, Brian.
Lovely. Sorry for that, all this technology. Okay, good day, everyone. What I hope to do is to show you that detecting the radiation from neutral hydrogen is a fun challenge for those of us with an interest in microwave radio, and striving to receive it can teach us lots of useful lessons that we can apply to our other microwave activities. I'm going to go a little bit further than that and show how you can start to pick out the structure of the galaxy that we live in as well. I'm going to start with a very brief introduction to spectral lines in astronomy, and the hydrogen line in particular. Then I'll cover what is needed to observe and study the hydrogen line based on my rather primitive system here, which is rather dated now. And I hope it might inspire some of you to think how it would be much better to do all this with software-defined radio, but unfortunately I don't have the skills to do that. And finally, I'll cover what we can expect to observe from the backyard and why it's of scientific interest. So, talking about spectral lines, these have a long history in astronomy and have enabled astronomers to identify the elements present in stars, and more recently, even in the atmosphere of exoplanets. And thinking of the Bohr model of the atom, emissions and absorption lines are caused by the transition of electrons from one shell to another, absorbing energy as they are raised to a higher energy state, and then emitting that energy on a very precise wavelength when they fall back. Most of these lines used by astronomers in the past anyway have been in the visible part of the spectrum, but there are similar emission lines in the radio part of the spectrum, and of course it's one of these that I'm going to talk about today. Here's a list of some of those spectral lines, and right at the top of the list is hydrogen, and that very obligingly emits radiation on 1420.405 megahertz. And as it's the most abundant element in the observed universe, it's far and away the easiest for us to detect with a small backyard radio telescope. Okay, the mechanism that causes the emission of the hydrogen line is slightly different to the one described in the Bohr model. It's caused by the spin of the electron about the proton in the hydrogen atom, flipping from one direction to another. One direction has a higher energy state, and incident energy from sources such as nearby stars or what have you can cause it to flip into the higher energy state, and then it will flip back to the lower energy state. And as it does so, it will emit a photon of energy on this very precise wavelength or precise frequency. Excuse me. This is reckoned to happen only about once every few billion years for a given atom, but there's so many billions of atoms out there in space that it's really quite easy for us to receive. Of course, if all this hydrogen were and it wasn't moving, we'd hear a nice T9 note on the 1420 megahertz. But of course it isn't, it's dispersed, it's moving. It tends to be gravitationally bound to the massive structures of the galaxies. And so the frequency is Doppler shifted. But when we examine it, we'll find that there are peaks in the noise that we can detect, which relate to the peaks of hydrogen linked to the different masses of hydrogen with similar observed velocity. So if we're to make interesting observations of the hydrogen line, what do we need? Well, we need an antenna with an aperture of 2 meters or more. You can probably detect hydrogen with a smaller antenna, but the aperture not only detects how much power you're going to collect, but it also determines the pixel size. So really, to make any sense out of the structure, it's a good idea to have an antenna of 2 meters or more if you possibly can. You're going to need a very sensitive receiver with a low T-cis, including the antenna, any noise added by the antenna. You're going to need a means of displaying the spectra around 1420.405 megahertz. And you're going to need a detector with good resolution and linearity across the frequency range of interest. So you don't want any lumps and bumps in the frequency response. So this is the setup that I use, which is a 3.7 meter dish, which I use for EME on 3.4 through to 24 gigahertz. And this has an effective beam width at 1420 megahertz of about 5 degrees. And that allows a reasonable resolution of about 2 degrees. So the pixel size is about, think of the pixel size as about 2 degrees. So pretty big in astronomical terms, but you'd be amazed the detail you can pick out even with that. The gain at 1420 megahertz is around about 30 dBs. If it were a 2 meter dish, we'd have a gain of about 25 dBs, and the 3 dB beam width would be about 8 degrees. So the pixel size would go up to 4 or 5 degrees. course, it's always nice to have a bigger antenna, but unfortunately, most of us are stuck with limited space. So, system design priorities are to minimize TSIS, maximize the sensitivity to small changes. You're only going to see small changes in levels, and detect linearity, flatness across the frequency range. And for galactic observations, that is our own galaxy, the frequency coverage we need is about 1419 to 1422. That's plenty. If we were able to study other galaxies, we need a much bigger frequency range due to their much higher velocities relative to us. Excuse me. Must stop smoking those woodbines. Right, receiver bandwidth. As we're measuring noise, of course, we want a maximum of bandwidth to collect the maximum amount of power so that we can run a sensible detector. This is the formula for noise power. And there's only one parameter in there that we have any control of, and that's B for bandwidth. So you want a maximum bandwidth in your detecting system to collect the maximum amount of power. But we're going to want to resolve frequency as we're interested in the velocity of the observed hydrogen. A reasonable compromise of bandwidth is about 10 to 15 kilohertz. And it turns out that a pretty standard PMR type FM filter is quite handy for this. It's just about right. And as you'll see, most of my system, or much of my system, is built from bits out of the come handy box in the workshop. The next thing we need to think about is all the way through this really is system is bound. You start there with the feed horn. I tried a couple of types of feed horn. The QMR type feed, which you see lying on the ground there, is the one most commonly used. It's relatively simple to make, and that's quite commonly used in amateur radio astronomy. But with a dish of, with an F over D of about 0.43, which is what my dish is, it fully illuminates the dish, and there is some pickup of ground noise beyond the periphery of the dish, significant pickup of ground noise. So I made a dual mode feed horn, scaled from the W2 IMU design. This slightly under illuminates the dish, as shown by this diagram. You can see it. It's 10 dBs down, quite a long way before the edge of the dish. But the advantage in terms of reduced spillover and therefore reduced pickup of ground noise was well worthwhile. As mentioned before, I use my dish for EME on 4 bands, and the 2 higher bands, I actually use it, well, the 2 lower bands I use as a prime focus dish, and then 2 higher bands, it runs as a Cassegrain. So I needed an easy way of changing the feed for the 2 EME bands and replacing them for the with a Cassegrain for the 2 higher bands, and an easy means of putting the hydrogen line feed into the system. And for that reason, the feeds are mounted on a servo actuated trolley here. So they can be positioned fairly rough and ready, and then they're brought into focus by operating the servo. And that's achieved by pointing at the sun and tuning for maximum noise from the sun. Still thinking about keeping the TSIS down to an absolute minimum. This is the probe that goes into the waveguide section of the feed horn, and you see it has no socket on it. We come straight in on semi-rigid cable. I made a flange which bolts onto the outside of the waveguide section, and the probe is attached directly to the semi-rigid cable, and there's just one SMA socket before it goes into the low noise amplifier, which is up here. Ordinarily, that probe would be inside here, feeding into the low noise amplifier. The image on the right, I thought you might just be interested to see as part of the process of rolling the cone to make the dual mode type of feed horn. Looking inside the other part of the outdoor part of the system, here is the low noise amplifier, which is one of Sam's VLNAs, which was very satisfactory. And on the left is the down converter, a Kuna Electronics down converter for the hydrogen line. This stuff in the middle, don't worry about that. It's actually a Dickey switch. At one time, I was thinking of switching references and things during measurements, but I went off that idea. So effectively, the low noise amplifier connects directly into the down converter. Now, the down converter sends a fixed IF back to the shack, or as the astronomers prefer to call it, the observatory, so that there are no artifacts introduced, frequency-dependent artifacts introduced by the lumps and bumps in the cable on about a 25-meter run down ducts and round the houses back to the shack. So to do that, the local oscillator is supplied from indoors. So the local oscillator comes in here, and the IF comes out here by the look of it. Back at the shack end of the most of my stuff is built out of bits from the Come Handy box. The signal, the IF signal, fixed IF signal, comes through a programmable attenuator. Actually, that's overkill. A fixed attenuator would have been fine. Its function is to make sure that you get the signal level into the most linear part of your detector. You want the best linearity you can manage. After the attenuator, it goes into this board here, which is actually, it's a very much modified Wooden Douglas FM radio, if you like. It was originally UHF. I converted it to VHF. The main thing I'm doing is using some gain in here and its filter. I've removed the FM discriminator and replaced the gain from that by a couple of dual gate MOSFET stages, which then feed a diode detector. And the diode detector then is a little bit of signal conditioning. And from there, it goes into an A to D converter. Nothing particularly special about that. And all this is controlled by a PIC. The PIC also controls a SI570 programmable VFO to generate, I think it's a quarter of the local oscillator frequency that's sent out to the output is multiplied out. Another feature here is a real-time clock. That's there. You'll probably see later on in the presentation that you need to date and time stamp your observations. We'll see why in a minute. So there's the outdoor unit mounted on the dish with the horn ready to go. And just to run through here again is the block diagram. Outdoor unit, local oscillator fed out to it, IF coming back, attenuator, fixed IF, AM detector, PIC controlling it all, programmable oscillator, and a real-time clock. The function of the PIC is going to be to scan across the parts of the band we're interested in, and as it does so, it sends the data out as a CSV to the observatory computer, of which more in a minute. Actually, this is what the units look like. The outdoor part is This is the sort of bottom of the outdoor part. You see the IF out, local oscillator in, and some control and other connectors. And about the only thing on the indoor receiver that's not controlled by the computer, there's a meter there that simply shows you the detector level, so that you have some confidence when you're making an observation that things are working and you're still within the reasonably linear part of the detector range. Excuse me while we have a lubrication. So the data that looks something like this. For each pixel that we're observing, we scan across the spectrum. Here is just a sample. We're scanning at 10 kilohertz steps, and we have as many of those steps as we need to cover the bit of spectrum that we're looking at, which, as I say, is likely to be in the range of 1 to 2 megahertz. Here's the detector voltage, and the other column there just contains the fixed attenuation, which was in there to get it into the linear part of the detector range. So what are we going to see? Well, this is what we're likely to observe if we point our dish in the galactic plane, so along the galactic equator at a galactic longitude of about 84 degrees, which is, to the astronomers amongst you, is roughly Deneb. We see 3 bumps associated with the arms of the galaxy. There'll be much more about that in a minute. But here's the scale, detector output, which I've converted to dBs. And the scale at the moment is simply frequency. This isn't terribly helpful in astronomy terms, because in astronomy, the unit of brightness is antenna temperature. We can easily measure the changes in Y factor, and we can calculate the antenna temperature from the Y factor using this formula here. By the way, various formulae and links that I've got in the presentation here are listed on a PDF, which I've put on my website. I'll give you a clue how to get there at the end. But that's the formula to calculate antenna temperature from the Y factor. So now we've converted the scale to degrees Kelvin, antenna temperature. This is the same observation. Sorry, it's missing the 84 up here. That's the same observation. And replaced the horizontal axis with topocentric radial velocity. That's the velocity that we've calculated from the Doppler equation, putting into the Doppler equation the known rest frequency for hydrogen. And it's here we are displaying it in the form that red shifts, that is stuff going away from us, are considered positive, and blue shifts, that stuff coming towards us, are negative. That's the convention in astronomy. And you notice several things here. One is that these 2 arms of the galaxy are apparently coming towards us. And the other thing is that the hydrogen here, which is associated with the local hydrogen immediately in the arm of the galaxy in which the sun and the solar system are located, is not quite at 0 yet. We'll come back to that in just a moment. So to do that, we need to correct for what is known as the local standard of rest. This is the sort of agreed correction for the part of the galaxy that we live in. And this takes into account, in order to take this into account, you need to know the date and the time of the observation, the direction of the observation. You need to know the latitude and longitude of the observatory. And then you can calculate the correction to the velocity reference to the local standard of rest using a calculator that's online. And again, the link to that is on a PDF, which is on my web pages, and I'll show you how to find that later. So the way I've calculated that by pasting data from the receiver into a template of a spreadsheet previously prepared. So here you see the frequency scale that was pasted in from the receiver. It had simply been logged on Hyperterm or something, and then pasted into the spreadsheet. The detector voltage was pasted into the spreadsheet, and so was the attenuator value there, which we're not going to use anyway. The spreadsheet has calculated the topocentric velocity here in kilometers per second. And you notice that in astronomy, all numbers tend to be astronomical, stuff moving at 85 kilometers per second to start there. The other columns, this part here is purely a correction for the frequency response of my system. It has a slight slope on it across the part of the spectrum that we use. So I simply take a number of the measurement. I measure the detector level, which should be, for example, here it's just noise at the start of the scan, and at the end of the scan, calculate a slope which corresponds to the noise floor in this column. This column, the topocentric velocity has been corrected to the velocity reference to the local standard of rest. That number that corrects that is up here somewhere. And that was simply calculated after the observation offline, and the number put in there to bring all those velocities into the local standard of rest. Here is a column containing the Y factor. Not much going on to begin with, but as you go down, you see we're up to sort of 3.5 dBs of increase in noise level. And in this column here is the calculation converting that into antenna temperature, and that's what's being plotted on the chart here. Now, in order to make sure our system is calibrated, there is a very useful set of data available from the University of Bonn, which is their lab survey. And this is a complete survey of the hydrogen line. It was made using two telescopes, one of which I believe was Gringaloo, so it's got an amateur radio connection there, and I think the other one was a telescope in Chile. But the really good thing about this link that is again on my page at the end of the presentation is that you can specify the beam width of your antenna, and it will present you with data in the same format that you saw in my spreadsheet for that observation. And you can use this for calibration purposes. And if you can see, the blue line in this is my observation, and the red line is what the lab survey predicted for an antenna with my beam width of my antenna. And I think that corresponded with a T-sys of about 53 Kelvin. So it's very useful to know that you can accurately calibrate your system. Now, the process of each observation is for a single pixel. So this is a pretty time-consuming business if you're going to start making enough to unpick the structure of the galaxy, but it's great fun, and astronomers love making observations. So here we go. This is what's going on the the screen when observations are being made. That at the background here is a table showing the galactic latitude and longitude being observed, that you want to observe. So that's a 1 pixel being observed there. My tracking program speaks in terms of right ascension and declination, that is celestial coordinates, not galactic coordinates. So you need to first convert the galactic coordinates into celestial coordinates. Again, there are online calculators that do this. I don't think I've listed that on my PDF, but they're easy enough to find. If you find celestial, if you Google celestial coordinate converters or something, you'll soon find one. So this tells us the right ascension and declination, which are entered into the tracking software. The dish is enabled and it slews off to the right direction. And once it's arrived, it will continue to track, updating every 10 seconds until you tell it to do something else. At that point, you can start the observation, and here is a screenshot of the data coming out of the receiver. And you see in this particular case, it's going in 5 kilohertz steps. Here is the detector voltage, which is going up and down as it finds hydrogen with different amounts of hydrogen radiation and different frequencies. So you can analyze this data in lots of different ways, and the various members of the group that we had making these observations a few years ago came up with various interesting ways of looking at it. Here is a particular set of observations at the galactic longitude of between 60 and 70 degrees. If you go back to 0, that's looking in towards the center of the galaxy from the sun, and it goes round from there. We can't observe the center of the galaxy from the northern hemisphere. But you see here, we've got longitude in this direction on this scale, velocity on this scale, and this scale is antenna temperature. And we see that there is a peak roughly at 0. That's our local hydrogen. And by local, I mean out to about 5,000 light years. If you think of the radius through our particular arm of the galaxy, out to about 5,000 light years is the local stuff. And as we look along, we can see the another what appears to be perhaps some other hydrogen merging with the local hydrogen. Over this side, we see some associated with another arm of the galaxy starting to build up. So that's one way of looking at the hydrogen around us. Here, this image, a constant longitude, and scanning through latitude, only by plus or minus 12 degrees in this particular case. You quickly, once you start looking at this stuff, you quickly find out how very, very flat the galaxy is. And so here are some observations going round from 12 degrees below the galactic plane to 12 degrees above. This is the local hydrogen. Now we'll take a quick trip around the galaxy and see what happens. I don't know if you can see these yellow lines here. Those shows the field of the observations being plotted here. And here's the results of those observations, and you can see distinct peaks occurring. And as we go around, you'll see they move. As we're looking through different bits of the structure of the galaxy. So you get the general idea. You can start to use various approaches, graphical approaches, to try and understand the structure of the galaxy. But you can also start to unravel the motion of the galaxy, ignoring the plots on the right here, which is simply the particular observation at different latitudes at fixed longitude. But you see that it's possible to calculate the radial, the orbital velocity of the bits of the galaxy that that you're observing. And this is where it starts to get a bit interesting, because we find that the galaxy is not behaving as we would expect it to. We can look at this image. By the way, the image is a NASA artist's impression of the galaxy. If you want to find it, you can find it on the archives of APOD, Astronomy Picture of the Day. It's a lovely picture, but it is an artist's impression. Obviously, to get that image, you need to zoom off out of the plane of the galaxy by 100,000 light years or so. And even then you need a wide angle lens, I think. So you can measure the velocity, or you can indicate the velocity, even with observations made with a sort of backyard radio telescope of something like 2 or 3 meters. And what we'd expect is that the galaxy would behave something like the solar system, because we can see that apparently most of the mass of the galaxy is residing at the center, a bit like the solar system. And we know that with Kepler's laws and the Newtonian physics, this is what we expect to see. We see the planet closest to the sun is whizzing along at between 45 and 50 kilometers per second. And as you go further out, they get progressively slower. Earth is loafing around the sun at mere 30 kilometers per second. And so it goes on. And you would expect to see that with the galaxy, rotation of the galaxy. But in fact, we don't. We see that the distribution is much flatter than that. The scale here is in velocity in kilometers per second here, and here is the radius, the distance in light years from the center of the galaxy. These are actually the results that we made, and they show that that it's a bit flat, and that tells us that there's something unusual going on, and rather demonstrates the need to come up with explanations like dark energy and dark matter. And I think it's rather cool, if you like, that you can demonstrate that from the backyard. Okay, I think that's the main part of the talk. I'm happy to try and answer questions if anybody's got any. But if you're looking for any of the formula that I've used or the links, probably the easiest way to get to them is to put G4NNS into Google, go to the home page, and there you'll find a link. It's this link here, actually. Or if you prefer to do it the hard way, you can type in my homepage web address and find it that way. I'd like to give credit to the various members of the Hydrogen Line Observing Group who helped with the observations, and particularly with the processing of the data that I've shown you here into various graphical forms. That project sort of came to an end for various reasons, and there's no reason at all why it shouldn't start up again, and more interesting possibilities could be explored regarding the processing of the graphical data and then presenting it in different ways. So, okay, Neil, I see you there. I'll stop screen sharing and pass it back to you.
Right, thank you very much, Brian. That was a very, very interesting talk. Fascinating what you've been able to achieve with your system in your backyard. Now, as someone who's, well, not very experienced in EME, unlike yourself, have you measured the sun noise that you would get with your hydrogen line setup?
I have indeed, and you're going to ask me what it is, and I honestly don't remember. It's one of those throwaway things. I use the sun for focusing the dish, but as I've got so much better ways of calibrating the system using these calibration points in the hydrogen line, I've never actually bothered to find out what the sun noise is. Of course, as you know, as a good EMEer, the first thing you check with your system is what is the sun noise, check the solar flux, and then you check what the moon noise is. But I have to confess, I haven't done that. I think moon noise would be rather disappointing on 1420 megahertz with a 3.7 meter dish, I'm afraid.
Okay, thank you, Brian. John, do we have any questions that have come in via the chat box on the streamer?
Yes, Barry V4MA has some questions. Is the peaking on sun noise done on maximum noise or the ratio between sun noise and cold sky?
That's a very good question, Barry. I tune for maximum. I must admit, I tune for maximum. It's a pretty insensitive way of doing it, but it seems to work.
And the second question from Barry is, how stable is the analog system gain? Is that why the Dickey switch was not required?
Yeah, I think that about sums it up. It is very stable. I'm very happy with the very simple diode detector. There's a little bit of gain after it, of something really sophisticated like a 741 op amp or something. Yeah, it really is very stable. I expected there to be, you know, big drifts. That's why I had the programmable attenuator in there. In actual fact, you don't really need it. I dare say that some, you know, if you're talking about really long-term observations, then yes, there'll be temperature changes and so on. But typically observing a single pixel takes from memory about 15 minutes, and everything seems pretty stable over that sort of time frame.
And the final question from Barry is that tracking software custom made? And do any of the normal EME tracking programs, are they usable?
It is homemade with a lot of help from Robin G8 to APZ, and but yes, the F1EHN's program I think will do precisely the same thing. And had I had more time, I would have said the other go-to place for hydrogen line astronomy is Jean-Jacques F1EHN, and very good evening to you if you're listening. And he's got all sorts of useful stuff on his website, but I'm sure his tracking software is absolutely fine for the purpose.
Okay, question from Heather M0HMO. How did you get the radius information that you used for your last plot? Sorry,
say again.
How did you get the radius information that you used for your last plot?
That's a very good question. The guy who did it actually, I think we used the artist's impression that you saw. It has got a scale in light years on it. The galactic artist's impression from Apr-2021 actually has the radial distances on it.
Right, okay, that's all the questions on the streamer so far. And if anybody else would like to ask any questions, please type on the streamer service.
Well, I don't see anything coming up at the moment, John.
No, nothing at present.
So I think that concludes Brian's presentation tonight. Thank you everyone who joined us this evening. Very, very interesting. I'm in the process of installing a new EME dish, and perhaps I might have a go at hydrogen line astronomy sometime in the future. So thank you very much, Brian. Well, this talk by Brian tonight was the last in the current series. We've the committee has agreed that it's been very successful, but we're going now to have a break over the rest of the spring and the summer, and we will start the talks in the autumn, I guess, probably in October. But in order to do that, we do need speakers who are willing to put together a presentation and present on Zoom. So if anybody watching has got any anything that they would like to present, please let us know. Or if you've got any suggestions of talks you would like to hear, or think the subjects you'd like to hear that are related to microwaves, again, please let us know, and we can then see if there's anyone out there who has a talk available or is willing to put a talk together. So I'd like to thank all our speakers that we've had over the last 6 months. I think they've all been extremely good, and we look forward to a similar series of talks next autumn, winter. Before I finally close, just a reminder that on Sunday morning at 10:00 British Standard Time or 900 UTC is the annual general meeting of the UK Microwave Group. So if you can, please join us, and we've got a committee to elect and officers to elect, and I believe that Barry G4SJH will be giving after the AGM will be giving us an update on the situation regarding the 23 centimeter band and the likely impact of radio location systems such as Galileo. It's a fairly hot topic, because in the last week or two, amateur access to the 23 centimeter band in Finland was totally withdrawn. So we're hoping to get an update from Barry. So I would just like to thank Brian again, and also John G3XTY, who's in the background controlling everything and making sure everything gets linked up to the BAT streaming service. So thank you for that, John, and I wish you all a good night, and hopefully see some of you on the Zoom call for the AGM this coming Sunday. Good night from Neil, G4LDR.